Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. Dynamic turn-on and turn-off. In today's session, I'll be covering dynamic turn-on and turn-off characteristics of SCR, natural commutation and force commutation of SCRs. Dynamic characteristics of SCR includes turn-on and turn-off time. Firstly, the speed of operation of SCR can be determined by using SCR turn-on and turn-off time. And here in this session, we will be in detail discussing about turn-on characteristics as well as turn-off characteristics of SCR. And here, for an instance, I've taken this SCR as a switch. And let us see in detail what is the actual operation which is being undergoing during the turn-on and turn-off time. And if you consider turn-off of SCR, in that case, it will be acting as an open switch, and whatever the voltage which we are actually applying across this particular SCR will be appeared across this particular open circuit. And here, the voltage will be high and current will be less. And if you consider turn-on switch, during turn-on, it acts as short circuit, and whatever the voltage which we are applying, voltage will be less and the current starts increasing. That means during turn-on time, the current will increase and voltage will decrease. Whereas during turn-off time, current will decrease and voltage will increase. In order to understand, firstly, we need to understand this simple thing first. And then, turn-on characteristics of SCR. The time taken for SCR from forward blocking mode to forward conduction mode is called turn-on time of SCR. And here, this turn-on time includes delay time, rise time, and spread time. And here, as we have discussed previously, the moment when we intend to turn on the SCR, at that instant, we will be applying the forward voltage such that here, see, anode is made positive and cathode is made negative. And in this case, if you see, this P terminal is connected to the upper P terminal is connected to positive and outer N layer is connected to negative. That is the reason here J1 and J3 are forward bias and J2 is reverse bias. That is, here inner N layer is actually connected to positive terminal and inner P layer is connected to negative terminal. That means that is the only reason here J2 is reverse bias and it forms a depletion layer over here. That means it is acting as a potential barrier which is stopping the free flow of electrons. And that is the reason there is the mode where it is acting as forward blocking mode. That means it is ready to conduct but not at conducting state. So, in order to bring the SCR into the conduction state, here we are actually applying the gate triggering pulse in order to bring the SCR into the conduction state from forward blocking mode. And under such condition, the moment when we apply the gate triggering pulse, the gate current flows in this direction. And here the electrons, if you see here, lower N layer, that is which is connected to cathode, which will be usually heavily doped. And the electrons from this particular N layer will be moving towards the P layer, and from P layer, these electrons will be jumping into the N minus layer. And in this process, the recombination of electrons will take place with these holes, and because of which the width of the depletion layer J2 will be getting narrow. And here, because from P layer, electrons are jumping into the N minus layer, and in P layer, electrons act as minority charge carriers, and since these minority charge carriers are jumping into the N minus layer, this acts as leakage current. And because of the gate current magnitude, more electrons will be moving into the jumping into the N minus layer, and in this process, the more leakage current flows. And this is a cumulative process, and because of which the leakage current is increasing, and at some point, this particular junction J2 will be breaking. And because of which there is no barrier as of now, and the device comes into the conduction state. So the turn on time of SCR, it depends upon the gate current magnitude which we have actually applied, as well as the anode voltage, forward anode voltage which we are applying. It depends upon these two factors. So let us see. If you see here, the moment when we apply the required gate magnitude and the instant at which it becomes 90% of gate current, at that instant the anode current is rising, and here anode voltage is getting reduced, and finally it is reaching to the on-state voltage drop of the device. So during turn on of the SCR, at that instant current will be increasing and voltage will be coming down. And let us see in detail what is this delay time, rise time and spread time. Coming to the delay time, it is the time taken at the instant of 90% of Ig to 10% of Ia, or it is time taken for the fall of voltage from 100% anode voltage to 90% of anode voltage. During delay time, the current is very small and is associated with small area. By controlling gate current, only delay time is controlled, but whereas rise time and spread time is remain unaffected. If you see here, as in order to reduce the turn on time, we can actually increase the gate triggering pulse width, and during that moment the delay time will be getting reduced, and as well as turn on time will also get reduced, whereas rise time and spread times remains unaffected. And coming to the rise time, it is the time taken for fall of voltage from 90% voltage to 10% of voltage. This is the fall of voltage from 90% of voltage to 10% of voltage, or otherwise it is the rise in current from 10% of anode current to 90% of anode current, and this is nothing but the rise time. See, during rise time, because of large di by dt, that is the current which is being increased is very high, and there is high rate of change of current with respect to time, and this high current is associated with small area which causes local hotspots or local heating. So due to this, SCR might be permanently damaged. Hence, an inductor is connected in series with the SCR. This inductor is connected in series with the SCR so that it limits the rate of change of current which is flowing through the SCR, such that the SCR will be prevented from the damage, from heat damage. Hence, an inductor is connected in series with SCR. Practically, instead of inductor, a saturable reactor can also be connected, and that is usually more preferable during rise time in order to protect the SCR. Power losses are high because high current is associated with high voltage. If you see here, current is high and voltage is less, and because of which the power losses associated in the device will be very high. See, these are the power losses which are associated during the rise time, and in order to protect our SCR from heat, that is the reason we are connecting a inductor in series with the SCR. Coming to the spread time, it is a time taken between 90% of Ia to 100% of IA, or it is a time taken between the voltage 10% to on-state voltage drop. That is, see, during spread time, the current, anode current reaches from 90% to 100% of its final value, or otherwise, spread time, it is also defined as the time taken by anode voltage to reach 10% of its, from 10% of its final value to on-state voltage drop. This is the on-state voltage drop of the device, and the on-state voltage drop of the device will be about 1.5 to 2 volts. This is nothing but spread time. So the total turn-on time is given by the summation of delay time, rise time, and spread time. Turn-off characteristics of SCR. That is the process of bringing the thyristor from forward conduction mode to forward blocking mode is nothing but turn-off time of the SCR. Once the SCR starts conducting, gate has no control over it. Even if we remove the gate triggering pulse, the SCR will remain in the conduction state because it will be attaining the value so-called latching current. And once the latching current is reached, gate has no control over it. Even if we withdraw the gate triggering pulse, the SCR still remains in the conduction state. So the device can be brought back to blocking state only by reducing the forward current, that is by reducing anode current less than that of the holding current. Only in that case we can bring back the diode thyristor into the conduction state. So here process of turning off of SCR is called commutation. And if forward voltage is applied, immediately after reducing anode current to 0, it will not block forward voltage and it will start conducting again, although it is not triggered by a gate pulse. So this process is called commutation failure. When the forward voltage is applied, the thyristor should be in a position to block that particular forward voltage. So for that purpose, what exactly here it need to happen is, see, when the SCR is coming into the on state, turn on state, whatever the charge carriers, it is spreaded throughout the SCR. And we need to remove these particular trapped charges, and recombination of these electrons need to take place such that it will be in a position to block the forward voltage. So for that purpose, it is necessary to keep the device reverse bias for a finite period of time. So here we are actually, see here, anode current is brought down to 0 initially, and the moment it has become 0, we will be applying the reverse voltage. And reverse voltage will be applied such that the current will be reduced. This happens during the reverse recovery time, and then later the recombination of electrons will be taking place during gate recovery time, and this time is sufficient. Later, if we apply the forward voltage, it will be in a position to block the forward voltage. And even if you see beyond which there is the forward voltage, and now we can apply the forward voltage conveniently such that it will block the forward voltage. So that is the thing. And here if you see, initially from the outer P layer and outer N layer, the electrons, see, in the P layer, the majority carriers are holes, and these holes will be attracted towards the negative terminal whenever the reverse voltage is applied. In order to turn off the SCR, at that instant, these holes in outer P layer will be attracted towards the negative terminal. And if you see the electrons in outer N layer, these will be attracted towards the positive voltage, such that the trapped charge carriers in the outer P layer and outer N layer will be removed. Whereas the inner N layer and inner P layer still consists of trapped charge carriers, and these will be recombined later. Okay, in that case, it will be in a position to block the forward voltage. So therefore, it is necessary to keep the device in the reverse bias state for a finite period of time after anode current has reached zero, so that SCR gains the capability to block the forward voltage before a forward voltage can be reapplied, during which the excess carriers from 4 layers of SCRs will be removed, including sweeping of electrons from this particular outer P layer and electrons from outer N layer, and then later the recombination of these electrons in the inner N and P layer around J2 takes place. Turn-off time defined as minimum time interval between the instant at which IA becomes 0 and instant at which device is capable of forward voltage. That is, turn-off time is equal to summation of reverse recovery time and gate recovery time. Let us see these turn-off characteristics in detail. See, at this instant, at T1, anode current becomes 0, and this instant we call it as T1. And now, from this instant, T1, if you see, this is the procedure where during from T1 to T3, at this instant, outer electron holes, charge carriers from outermost layer, that is from outer P layer and outer N layer, the charge carriers will be removed. And at this instant from T3 to T4, the recombination of electrons in the inner N layer and P layer will be taking place. So, if you see here, removing charge carriers from outermost layers, that is from outer P layer and outer N layer, is easy. It is because P layer is connected to negative and N layer is connected to positive. Because these are holes, these will be easily attracted to the negative terminal, and electrons from N layer will be easily attracted towards the positive terminal. So these trapped charges from outer P layer and outer N layer can be easily removed, whereas the inner N layer and inner P layer, it will be difficult. So recombination will be taking place from this instant called T3 to T4. And later it will be able to block the forward voltage. So here at this instant T1, anode current becomes 0. During TRR, at this instant T1 to T3, anode current flows in the reverse direction. Due to stored charge carriers. At T2, reverse voltage is developed and reverse current continues to decrease. At this instant called, see here reverse current is increased, and at this instant almost 60% of trapped charge carriers from outer P layer and outer N layer will be removed, and later current will be getting reduced. And at this instant called T3, the charge carriers in N- layer and P layer will be recombined. That is from instant T3 to T4. At instant T3, reverse recovery current removes charge carriers from junction J1 as well as J3 between T1 and T3 are able to block the reverse voltage. However, thyristor is not yet able to block the forward voltage because of the trapped charge carriers which are still present at this junction J2. During T3 to T4, these charge carriers combines, and at T4, recombination is complete. Therefore, a forward voltage can be reapplied at this instant. SCR turn-off time is the interval between T1 and T4. Time varies in the range of 10 microseconds to 100 microseconds. This is the turn-off time of the SCR. And turn-off time required for device is sum of duration for which reverse recovery current flows after application of reverse voltage and time required for recombination of all the excess charges in inner two layers of the device. Circuit turn-off time is usually greater when compared to that of the device turn-off time. See, this is the circuit turn-off time and this is considered as the device turn-off time. And usually this circuit turn-off time is greater when compared to that of the device turn-off time. So it is suggestible for the SCR to remain off for some more time, and it is better to apply the forward voltage at this instant such that we can avoid the commutation failure. And it leads to the safe operation of the SCR. Otherwise, device will turn on at undesired instant known as commutation failure. And here 50 to 100 microseconds are slow switching or phase control type SCRs, and 10 to 50 microseconds are fast switching or inverter type SCRs. And turn off characteristics. Whenever the reverse voltage is applied at this instant, the current reverses its direction and junction J1 and J3 will be reverse bias. This time is called reverse recovery time. And the time for holding negative voltage across the thyristor to ensure that thyristor is not yet turned on is called gate recovery time. And the turn-off time is the time taken for SCR to achieve forward blocking state after communication is initiated. That is equal to reverse recovery time plus gate recovery time. Hope now turn-off characteristics are clear. Now, what are the turn-off methods we have? We have natural commutation and forced commutation. Under natural commutation circuits, in AC circuits, current always passes through natural zero every half cycle. A reverse voltage will simultaneously appear across the device. See, if you see the AC waveform, which is sinusoidal in nature mostly, and it passes through natural zero every half cycle, and immediately after that, negative half cycle will be appeared. And whenever this negative voltage is applied, that will be appeared across the anode of the thyristor and it will be turned off naturally. This immediately turns off the device, and this process is called natural commutation, and this doesn't require any external commutation circuits. And the line commutated converters and inverters usually comes under this category. Coming to the forced commutation circuits, once SCR or operating in on state carrying forward current, they can only be turned off by reducing forward current below to that of the holding current, or otherwise we need to bring that into the zero. By reducing the forward current flowing them to zero, we can also turn off the SCR. And for that purpose, in case of DC circuits, for switching off the thyristors, forward current should be forced to zero by some external circuits. So this process is called forced commutation, or we can also call it as external commutation circuits. And these external commutation circuits includes inductance and capacitance. We call it as commutating components. And reverse voltage is developed across device by means of commutation circuits that brings forward current in the device to zero and thus turning off the device. Producing reliable commutation is a difficult problem. In the next session, we will see two transistor analogy and UJT unijunction transistor firing circuits. Thank you.